Welcome everyone! In this episode, we will uncover the hidden secrets of Pascal's triangle. But what is a Pascal's triangle? Pascal's triangle has each row containing one more element than the previous one. That's why it's called a triangle. In Pascal's triangle, the following rule applies. We start from the topmost point where we write a 1. From this point, we can only move downward, either to the right or to the left. The next numbers in the triangle are formed by adding the two numbers from which the arrows originate. For example, the 2 is the sum of the two 1s directly above it. The edge values are always 1, as they can only be reached from a single number, which is always 1. This pattern can be continued infinitely, but for now, we will examine only the first 5 rows. Let's see what happens if we sum all the numbers in each row. Write down the sums one below the other. Do you notice anything interesting? Each row's sum is exactly the double the previous row's sum. That's right. These are the powers of 2. Let's look at another interesting property. Write down the expansion of a plus b raised to the power of n. Some of these expansions might already be familiar from notable algebraic identities. Let's proceed row by row. If n is 0, then a plus b raised to the power of 0 equals 1. If n equals 1, we simply get a plus b. When n equals 2, we obtain the well-known binomial expansion. And as we continue increasing the value of n, do you notice something interesting? That's right, the coefficients in these expansions match exactly with the coefficients in Pascal's triangle. This means that the Pascal's triangle can help us easily determine these coefficients. Another fascinating fact is that each element in Pascal's triangle represents a binomial coefficient. The rule of constructing Pascal's triangle directly corresponds to the process of computing combinations. That is, selecting elements without considering order. The row number in Pascal's triangle tells us how many elements are we choosing from. The column number tells us how many elements we are selecting. Remember, both row and column indices start from 0. Now, let's return to the products. The values in Pascal's triangle and the coefficients of the products matched in each row. Therefore, the coefficients of the products can also be written in combinatorial form. In general, we can express the coefficients and the exponents using the equation above. This expression is known as the Binomial Theorem formula. Let's look at an example to understand how to interpret this summation equation. Let's see how to expand a plus b raised to the 4th power. So we substitute 4 for n. The summation should be interpreted as replacing k with all integer values from 0 to 4 and summing the results. In the first step, we substitute 0 for k, making b's exponent 0, so only a appears in the expression. Now comes the next term. The coefficient is obtained by selecting one element from 4. A's exponent decreases by 1, while b's exponent increases by 1. We add this to the previous term, and we continue this process up to 4. Using summation notation, this long expression can be written in a simplified form. This way, we don't have to write so much. Let's look at an interesting example. How many different ways can you read the word horse? In other words, how many ways can you reach the last letters? The values in Pascal's triangle precisely tell us how many ways can you reach each point. So, we simply need to write down the values from Pascal's triangle and sum the values at the last letters. In this case, the result is 16. So there are 16 different ways to read the word horse. From now on, you will be able to solve similar math problems easily. Finally, let's write down Pascal's triangle once again. Arrange the values along the left side. Now let's start drawing diagonals and sum the numbers along each diagonal. The first diagonal sum is 1, then again 1, then 2, followed by 3, then 5, and so on. These numbers are the first elements of a famous sequence. It is none other than the Fibonacci sequence. Interestingly, this pattern frequently appears in nature. For example, the spiral of a Nautilus shell follows this sequence, as does the arrangement of seeds in a sunflower. So, Pascal's triangle can even help describe and model natural phenomena. It is a mathematical symbol of nature. I hope this video helped. If it did, leave a like and subscribe so we can keep learning together. I'm curious about your thoughts. Write a comment and let me know what topic would you like to see next. See you soon!